All right, welcome back. This will be really quick. I just want to touch on some of the built-in array methods. There are many of them, and I want to stress that you do not need to know or memorize any of this information, but hopefully it makes sense as to how we arrive at the numbers when we're talking about big O notation. So again, I have a little emoji. You don't need to know all of this, but let's take a look. The first four we've already discussed, maybe not by name, but push and pop are constant time, adding and removing data to the end of the array of any array, whether it's one item or 10,000 or a million items, is constant time. It's easy. There's no re-indexing involved. We just put it at the end and give it a spot. That's basically it. Shifting and unshift, on the other hand, are a little more troublesome because we potentially have to re-index, well, not potentially, we have to re-index every element in the array if you're adding to the beginning or removing from the beginning. So as the number of elements grows to 10,000 or a million, then the number of things we have to reindex grows in proportion with that. So it's O of n, it's linear time. So those four, adding and removing, we've discussed. I'm trying to highlight the top four. It won't, no. Okay, well, that's the best I can do. So next up, we've got this little chunk of concat, slice, and splice. So all of these are O of n, linear time. And there can be some confusion. Something like concat takes multiple arrays and merges them together. And when we say O of n, you might think that that just implies, one array of n elements, and we're acting on that one array. What happens when there's two? Technically, you could argue that it should be, O of n plus m, where m would be the size of the second array. But O of n is fine. It's basically just expressing the fact that as these arrays grow that you're merging, so is the time that it's going to take. And it grows in proportion with the size, the total size of the new array at the end. What else did we have? Slice and splice. So slice is going to return a copy of part of an array, or the entire thing if you want it to. So O of n in this case refers to the fact that if we're trying to copy 10 elements versus 1,000 elements from an array, the amount of time it takes grows in proportion with that size, how large of a copy or how many elements we're trying to copy. So that's O of n. And then lastly, what we have? Splice. Where are you, splice? There you go. And splice is going to remove and add new elements. And splice is a little different because it's quite versatile. So we can insert at the beginning of an array. We could also insert at the very end of an array. We can replace given elements, but in general, it's O of n. If we're inserting in the middle of the array, we just simplify that to O of n. Remember, that does mean shifting and re-indexing everything that comes after it. So even if it's only in the middle, we would still say it's O of n, even if it's O of n divided by 2. We just don't care about that. So in general, a lot of things working with arrays are O of n. You may have noticed this one down here, sort. Array.sort O of n log n. So we're not going to talk about how this is derived, where the log comes in, where the n comes in, why they're multiplied. We spend a lot of time talking about sorting algorithms, and there are many of them out there. We talk about 6 or 7. I think it's 7, but I'm not positive. We talk about a lot of them. And some of them we talk about have a time complexity of O n log n. So we'll explain how we get there. But just know that the time it takes to sort an array is larger than just O of n. We have to make comparisons. We have to move things around. It's not enough just to look at every element once, and that's not enough just to sort it. It's a little more, sometimes a lot more complicated. So just keep that in mind. Again, we're not explaining how we get this, what the math is just yet, but it will make sense in due time, I promise, if you make it to the sorting sections. So sort is the slowest thing on here. And then things like map, filter, reduce, for each are all O of n. Those are looping over each element or doing something with each element, tallying it, doing a Boolean test, or just printing them out, or whatever we're doing. It just involves acting on each element or with each element. So as the size of the array grows, so does the amount of time it takes, O of n. So you can see almost everything that we could do with an array, all the built-in methods, not all of them, but all the ones listed here are O of n. Sorting takes longer. And then push and pop are super fast, just like with basic accessing using an index, super fast as well, constant time, and they're much faster than adding and removing from the beginning, as we've talked about. Okay, so that's a lot. And remember, you do not need to know all of this. Really, the main takeaways here between objects and arrays: 1, objects are fast at pretty much everything, but there's no order. 2, Arrays are great when you need an order, but still be mindful that it's better if you can do it to add and remove from the end and avoid adding and removing from the beginning, because that starts this cascade effect, hence the term shift and unshift, and everything has to be re-indexed. And the same goes to adding and removing from the middle. You start another cascade, a little tidal wave, and things have to be re-indexed after whatever you added or removed. All right, so hopefully that makes sense how we get to these numbers, what the values mean. If not, we'll be spending a lot more time talking about big O as we go. And this is really a primer for later on when we get to things like sorting, or when we talk about linked lists and how they're also an ordered data structure, but we can add and remove from the beginning and there's no problem. It's constant time. So how does that work? So we'll get there. That's coming up. That's all I have to say about arrays and objects. We're done for now.